So when we think about sort of planetary habitability, there's typically two questions that we have in mind. One is to understand our own history as a planetary species. How could life have originated here? What were the conditions that were present on the young Earth? But as we now know that the Earth is one of many planets, many potentially habitable planets, we're also trying to understand how often you could get origins of life on other planets. And one way of thinking about it is how often the kind of conditions we had present on the young Earth, how often we find those in our galaxy. Now, when an astronomer thinks about habitability, or when you hear talk about the habitable planet, it typically means like one very simple thing. Well, actually two, that it is a planet that is rocky, though, as probably many of you know, even that is a sort of contested whether it has to be rocky, which means it's not too big. And it is sitting at the distance from its host star, which allow you to have liquid water. Now, there are many ways in which this picture is both too restrictive and too generous. One way that it's too restrictive is, first of all, maybe you don't need a rocky planet. Maybe some other kinds of slightly bigger planets are sufficient. But the other is that maybe you don't need a planet at all. Maybe a moon would work just as well. Within our own solar system, we know there are several moons in the outer solar system that have liquid water. And if we decided that habitability just means that you can, at the right temperature for liquid water, it seems we should count those as well. My favorite moon is Enceladus, so the tiniest little water world that we have in our solar system, which has this very generous feature that it has a plume which is leaking some of its ocean into space, where you can actually pick up what is going on in its ocean. One of the exciting things that has been found in this plume, in addition to some organics, is molecular hydrogen, H2. There are currently several ideas of where both these organic molecules as well as the molecular hydrogen could come from. And one of the things that I've been working on before getting into sort of more astrochemistry with Nick here is to think about if what could be powering the chemistry on this kind of world where you don't have the light from the star, the UV photons. Traditionally, how people have been thinking about it is typically either hydrothermal chemistry or that you have radiation chemistry from the decay of radioactive nuclei. But another thing that's going on at Enceladus is that the core of Enceladus is getting squished. So the main source of energy at a small moon orbiting in a tight orbit around its giant planet is tidal dissipation. Now, tidal dissipation, it heats up the moon, so that's where you can get the hydrothermal vents. But it does another thing as well, which is really neat, or at least we think it does, which is that as pebbles and grains and boulders are rubbing up against one another as the core is getting squished, you would expect those grains, pebbles, boulders to form radicals on their surfaces as you're basically breaking the rock. These oxygen radicals can then react with the water to form both molecular hydrogen, molecular oxygen, as well as hydrogen peroxide. So now you suddenly have a rather direct sort of source of chemical energy on a moon like Enceladus. And then as long as you can get that molecular hydrogen, the oxygen, the hydrogen peroxide out from the core into the ocean, you can potentially drive the prebiotic chemistry there without going through sort of the extra step of first converting your tidal energy into heat and then drive the chemistry thermally. So this is something that we have been thinking about just the past few months. And one of the things that we're finding is that when comparing this way of generating molecular hydrogen to sort of other contenders, is that we do pretty well when thinking about what the instantaneous rate of something like production rate of something like molecular hydrogen, while when we think about the total production over Enceladus' lifetime, it's more unclear. And as you see, the bright blue and the light blue bar here for the rock grinding case comes from two sort of defensible assumptions that lead to orders of magnitude differences. But it's all to say that there are other potentially habitable environments within a planetary system than just the planets that are sitting close to their star. Whether we're thinking about a place like Enceladus, or we're thinking about sort of our traditional concept of habitable worlds, it is not sufficient to just be sitting at the right temperature or have the kind of processes in the case of Enceladus that gets you to the right temperature. Remember, the reason you want to sit at the right temperature is to have liquid water. So you want to ask yourself how often you actually get water on the planet, especially on these kind of Earth-like planets. And the other thing you want to ask yourself is, okay, the reason you need water is because water is a pretty great solvent. What do you want to dissolve? You want to dissolve organic molecules of different kinds. So the second question would be, how often do you get the kind of organic molecules that are interesting from an organism of life point of view, or are interesting as feedstock molecules from an organism of life kind of chemistry? And I want to think through these questions in the light of the chemistry that's going on where planets are forming. And we're going to do sort of 4 little vignettes thinking about how astrochemistry impacts what we know about the sort of future habitability of planets forming in these disks. The first one is just using chemistry to probe the planet formation process itself. So if you can think about the kind of molecules that you have in disks, it's going to impact what kind of planets you form, but it's also often the only way that we learn about those planets that are forming. And one of the things that's been really cool in sort of the past decade is that we have this amazing telescope in the Atacama Desert, ALMA, which allows us to do rotational spectroscopy on these planet-forming disks around young stars, which is pretty neat. And some of the things that you can see if you turn this telescope towards disks is what the distribution of different molecules are around these stars. So what you're seeing here in this sort of purple color, this is the thermal emission. It shows where the dust is. So this is sort of the future cores of planets. And then these sort of bluish images, each row here is a different disk, and each column is a different molecule. So you can really see it. We can tell where in the disk a different molecule is. And I'm just going to zoom in on one disk for 5 different species so you can see it a little bit better. And we see things like hydrogen cyanide, small hydrocarbons, and so on are quite abundant in these disks. Now, when we want to use this, we'll come back in how we're thinking about the impact of these molecules on sort of the chemistry of future planets. But if we want to use these molecules to just trace out planet formation, we need to understand how their formation relate to sort of the planet formation process. You see here, there's some different rings, other kinds of substructure. One of the questions you would want to know is, where do those rings come from? Can those be used to tell you something about the disk physics? The answer is maybe, or actively being researched, including by some people here, which is that when we look at how the molecules are distributed compared to the dust, we see some things that make sense and some that really don't. So what's shown here in the background are just the radial projections of the distribution of dust in these disks. So you see that there's some gaps where there's darker. And then on top of that, I've just drawn the radial profiles of some of the molecules that we were looking at. You can tell that some of the time, it seems like there is a dip in the molecules at the same place where there is a dip in the dust emission. So maybe you just less gas, less chemistry. But in other places, including in the same disk, there seems to be a peak in the emission where we have a dip in the dust. This is perhaps due to that you have increased photochemistry where you have less shielding from dust. So I would say we have explanations, or possible explanations, for many of the structures that we see, but we do not, at the moment, have sort of a predictive model if we get a new disk to be able to tell you when we should get this kind of chemical substructure and when we shouldn't. There is, however, one case which is maybe the most tantalizing to date, where we think we do have some idea what's going on. This is a disk around a slightly more massive star, sort of a star is around 2 solar masses. You see here the dust, so 2 nice rings. In one of these gaps, there is a planet that has been seen, or at least strongly inferred based on some scattered light observations. And then we have possibly a second planet that's carving out the inner gap. Now, if we look at the chemistry of this disk, on large scales, we see a lot of the molecules that I showed you before, things that don't have oxygen in them. Things like, if we looked at HCN, it would actually look quite similar to this. CS, HCN seems to be very abundant on sort of the large scales. But if we look at smaller scales, we see that there's also in this disk oxygen-bearing molecules, and in particular SO, which we think only shows up when you have water sublimating into the gas. So this is telling us that there's something that's getting the water into the gas. And in this case, it seems like there's this sort of big clumpy thing next to what's maybe is a planet. And then this is actually real, this little emission structure that's sitting next to the known planet. What's perhaps even cooler is that we also see a bit of SIS, which is not something we typically see. So the SI is that's silicon that's coming from destruction of grains, so the same kind of grains that are otherwise contributing to this dust emission. And that's really telling us that there is something pretty violent going on around the formation of this planet. That maybe we should, that is, I think, telling us that at least larger planets form in a more sort of interesting way than maybe sort of our toy models would suggest. Now, whether that tells us something about how small planets form, I think is unclear, but it should tell us something about how these larger planets that can host these moons that might be their own habitable environments, how they form in other systems. But I want to rapidly move on from thinking about chemistry as an instrument to thinking about chemistry for its own sake when talking about what kind of compositions of planets that we have. And the next thing that I want to consider is when we think about the elemental abundances of planets, how can we say something about this? This is something that shows up in a lot of exoplanet studies because it turns out that you have a very different chemistry if your atmosphere is oxygen depleted or oxygen rich. Also true for habitable planets, so potentially habitable planets. We just can't do that much with them yet, beyond trying to figure out what happened on Earth and Mars and so on. Other elements that we care about, nitrogen, sulfur, phosphorus, but I'm going to talk mostly about carbon and oxygen and how they are distributed in disks and may therefore contribute to the atmospheres of planets. At this point, we have to sort of zoom out a little bit and think about these planet-forming disks in the context of star formation. So when we form a planet, the first step towards both the planet and towards the chemistry that can end up on that planet happens in molecular clouds on very large scales. These molecular clouds, or at least clumps in them, collapse to form protostars that then form disks due to this preservation of angular momentum, and this is where planets are forming. So we have to take into account this sort of time axis and how we can inherit material from the earlier phases. The next thing which we already started to talk about is thinking about how material is distributed in the disk. You can imagine that if you form planets at different radii away from their star, they might end up with quite different abundances. And then the final thing is that we're going to have to think about how sort of microscopic physical and chemical processes result in sort of large-scale distributions or redistributions of material. Things like the simplest one being desorption of an ice off a grain and adsorption of a gas phase molecule on the grain, which is going to set the balance between gas and solid phase structures in the disk. If we start in this molecular cloud, we have a pretty good idea what the oxygen, carbon, and nitrogen are doing in terms of which species that they sort of exist within. Though when I say pretty good, the gray in each of these sort of pie charts are the things that we don't know. So for carbon, we're almost there accounting for where the carbon is, mostly in refractory carbonaceous grains and CO. For water, it looks worse. About a third of the pie is missing. The things we know are basically water, CO, and silicates, and some other things. There's speculations that a lot of this gray is hidden water, tied up in larger grains and boulders. And actually, for nitrogen, it is not as bad as it looks. We think most of this gray here is molecular nitrogen, which we just can't see because it doesn't have a permanent dipole. So this is going to be what you inherit from the molecular cloud, what you start with in your disk. And then the second question is going to be, how does the oxygen, carbon, and nitrogen become distributed in the disk if you don't have any additional chemistry? This is mostly set by the locations of so-called snow lines. These are the places in the disk where you pass a temperature threshold where species like water or CO goes from being mainly in the gas phase to being mainly in the solid phase. And one of the things that happens is that this results in a changing carbon to oxygen and changing nitrogen to oxygen ratio as you go across the disk. So basically, whenever you cross a snow line, you will take some hydrogen, carbon, oxygen, nitrogen from the gas phase and put it in the solid phase. And that's going to change both your gas phase and your solid phase elemental ratio. One prediction, which we're going to want to think about, is that if you look at the carbon to oxygen ratio, and we focus on the gas phase, so the thin solid line, is that as you go outward in the disk, you're going to increase your carbon to oxygen ratio and get to unity at large radii, because most carbon and oxygen, or most oxygen is carried by more like less volatile species like water, while a lot of the carbon is in CO. CO has one carbon, one oxygen, so you get a ratio of unity. This prediction is something that we can test with the same kind of observations that I showed you before. So this shows another version of the gallery of observations, again, rotational spectroscopy observations of these planet-forming disks. One of the things you can do is you can look at the ratio of emission from between CO and the non-oxygen containing molecule like C2H. And that's going to give you a probe of what the carbon to oxygen ratio is in the gas where planets are forming. It's a little bit more complicated than just putting one in the numerator and one in the denominator. But I think intuitively, it should make sense that if you increase the C over O ratio, you're going to increase the C2H to CO ratio in the disks. If you do this, you actually get that the C over O ratio in the outer disk is very high in the gas phase, higher than you can explain by just this kind of freeze-out model that I just showed you with snow lines. Somewhat unclear what this is due to. Two leading explanations is that either you get a lot of the refractory carbon, so the other sort of big reservoir of carbon into the gas phase, and that gets the CO ratio out, or like up to 2, or you're very efficiently removing oxygen from the outer disk, and we'll come back to one method in doing that in a bit. But in the meantime, I just want to quickly show you another way that we are measuring the CO ratio that gets us a little bit closer to where planets are forming. So these kind of C over O of 2, where we get that is in the gas phase in the outer disk. Think tens of AU to maybe 100 AU. We probably form some planets there, but that is not where most planets are forming. Another tracer that we see works better a little bit closer in the disk is using sulfur molecules, and especially SO over CS. And again, you see one has the oxygen, one has the carbon. It's the same idea. That ratio, it turns out, is more sensitive to CO ratio between like 0.1 and 1 instead of between 1 and 2, which is where the CS over SO works. And then the one that we have only really looked at towards a single disk, which I'll show next, is using deuterated species that have either just carbon or carbon and oxygen. The reason those are interested is that you only get high degrees of deuteration when you're at low temperatures. You're only at low temperatures in the disk when you're close to the midplane. And that is the gas that is primarily being accreted by planets. So that's actually the C/O ratio that you want to get to. The way that we look at this, just from a qualitative view, is that we take these images of the rotational line emission, of in this case DCO plus and DCN. If you have multiple lines of the same species, you can use that line emission to constrain how much of that species you have. This gives us then a ratio of DCO plus over DCN as a function of radius. And as you can tell, in this case, it varies by about an order of magnitude as you step outward in the disk. In the inner disk, the C over ratio, like the DCO plus over DCN ratio is low. That means that the C over O ratio is high. And with inner here, it's like the inner 60 AU. ALMA is not really sensitive, and it's closer than about 10 AU in these disks. While on the outermost disk, it's low, which is kind of the opposite what I told you before, that if we just again have this freeset model, you should have a low C over O ratio in the inner part of the disk and then a high C over O ratio in the outer part of the disk. What we are speculating is happening here is that we're actually here so far out in the disk that the disk is becoming transparent to UV light, and you're getting a lot of the ice back into the gas phase just through non-thermal processes. And that it's actually, this in some sense, is the outer part in our previous model. It just doesn't really show on this picture because of the sort of sensitivities of ALMA. So let's take one more step towards the question of habitability and habitable planets, and talk about water. So water is again, from an astronomy point of view, sort of what defines habitability. So you want to know, for a planet that has sort of the right physical characteristics, right temperature, right size, to potentially have oceans, how likely is it to have oceans? So that's going to be the next sort of story to look into. To do that, I first want to take another sort of step back and just say something about how we form molecules in these kind of very strange environments from a chemistry point of view. So if we're thinking about what kind of reactions are possible, if you're sitting down at 10 Kelvin at very low densities, the answer will be very few of the reactions that you are used to running in the lab here, including ones that you might run for atmospheric chemistry models. So if you're at low temperatures, you are not going to be able to tolerate any reaction barriers. Even ones that are small for sort of normal chemistry are just going to be way too high when you're sitting down at 10 Kelvin. And that means that if you want to form our AB molecule here, you need to bring one of the reactant into basically some sort of excited state. And the most common way to do that is to make one of them an ion. So a lot of the gas phase chemistry that's happening in astrophysical environments is happening through the mediation that you first ionize one of the reactants, and then you have that react. We have a second, which in some sense is even more of a serious problem, which is the density. The density is very low, which means that if you bring your A and B together, how do you get rid of the energy? I mean, at least the way that I like to describe chemistry to my astrophysics colleague friends is that you're just journeying on a potential landscape. And if you go down the potential and you don't lose any energy, you're going to bounce just right back up. And that is what happens if we're trying to just bring two species together, even if one of them is an ion, is that you have a much higher probability of bouncing back than falling down into the potential well and releasing some of that energy through a photon, which would be the way to get rid of the energy. The main way that nature solves this is having a lot of the chemistry, instead of happening in the gas phase, happening on the surface of small interstellar grains. These are the same grains that we already saw a couple of times when we saw this sort of thermal emission maps. And if A and B lands on the grain, they can walk around, meet, form, and then have the grain absorb that energy so the AB stays put. Turns out that also in the grain, you can actually tolerate small energy barriers. There also opens up some reaction pathways because of that. Many of the species that we are interested in form through this kind of processes. This is true also for water. We have run many experiments showing that the addition of hydrogen to either oxygen atoms, oxygen molecules, or ozone all lead to the formation of water. The way these experiments work is that you basically co-deposit your source of oxygen, hydrogen atom beam, and then you monitor the ice using something like infrared spectroscopy. You see the growth of your water, often accompanied by hydrogen peroxide ice, and then you put that into your astrochemical models to see how much water that you should form through this pathway. The answer is that you should show a lot, or like you should form a lot. And for those of you who haven't thought about this grain surface chemistry before, the Leiden group made a short video to try to help sort of guide your imagination. So this is the same dust grain that we have been talking about, around 0.1 micron. Oxygen atoms, hydrogen atoms are abundant in the gas phase. Because these grains are 10 Kelvin, once they land on the grain, they will stay there for some time. But these atoms are not bound super strongly, so they will be able to rattle around to find one another and form, in this case, water. Because this process is so efficient and oxygen and hydrogen are so abundant, you very quickly start building up a pretty large reservoir of water on these grains. And these grains are going to be the main reservoir of water as well as other volatiles as you're traveling through this star and planet formation journey. This is, so I showed you the experiment. I showed you sort of video based on those experiments. Here are actual observations of infrared transmission spectra towards one of these molecular clouds. Actually, not this molecular cloud. This is just the most photogenic molecular cloud. But for those of you who are used to doing infrared spectroscopy, you see the 3-micron feature of water showing up very brightly. So water is very abundant in the interstellar medium. We also have good evidence for that water survives this journey from cloud to planetesimal formation. We have evidence in our own solar system looking at the D/H ratio in water. Again, you get deuterium fractionation only at low temperatures. So when we see an excess of heavy water in the solar system, we can tell that a lot of that water must have formed cold that is formed in these interstellar clouds. So we have the water, but that doesn't mean that we have the water at the right place. We think we form Earth-like planets close to the star, and we form them exactly where there is no water ice. That is why you end up with a terrestrial planet instead of something like a mini Neptune. So that means that just because there's water in the disk doesn't mean that there is necessarily a lot of water sitting where the terrestrial planets are forming. Again, this water snow line shows where you go from having water in the gas phase to mainly in the solid. That is not the end of the story, however. These disks are dynamic, and there are 2 ways that you move material around. There are probably more. There are 2 ways that I'm going to talk about that you move material around. One is that grains decouple from the gas and start drifting inward. So if you have icy pebbles, they can drift in and dump a lot of their water in the terrestrial planet-forming region. And the other is that you have gas advection, both inward and outward. So any water vapor can also either spread out or sort of advect inward. One of the things that's super cool is that we now have a second really nice set of eyes on the sky for doing astrochemistry, which is the James Webb Space Telescope. So while ALMA allows us to do rotational spectroscopy, JWST allows us to do vibrational spectroscopy on these planet-forming disks. And one of the things that we had predicted coming in to sort of the James Webb era is that we should be able to tell the difference between disks where you have a lot of inward pebble drift and sublimation of water ice, and disks where you don't. And a proxy for which kind of disk you have should be the disk size. So this story is quite simple. Let's assume that statistically, you always sort of end up starting with one of these planet-forming disks that is of the same size. Then the only thing that's going to set the size of that disk is how quickly material move inwards. And that means that small disks are going to have had a lot of material drifting inward. Large disks are not going to have had a lot, probably because of these nice gaps stopping material from drifting inward. And that means that we should see that small disks have a lot more water vapor in them compared to large disks. And with JWST, this is something we can do. So Andrea Banzetti first looked at 4 disks and saw this. Then my student, Carlos, looked at 7 disks. And you can almost see by eye, there's a bit of an illusion that the large disks don't have that much stuff going on in their spectra compared to the compact disks. And when we look at these vibrational sort of infrared spectra towards disks, most of what we see is water. It is, however, a little bit of an illusion. You have to do more of a careful fit of the data because water comes in 2 flavors in these disks. Hot water that forms in situ and what we call sort of cold water, but it's water at sort of 200, 300 Kelvin, which comes from the indrifting of pebbles and then the sublimation into the gas phase. And if you look carefully, what you will see is that there's more blue in this panel and more red in this one. What this is telling you is that there's more cold water cold water vapor in the compact disks. We can look at this in a bit more statistical of a way, though with 7 disks, statistical is a word with, say, somewhat of a fraught meaning. And we can ask of how does the hot and the cold water mass sort of depend on the disk characteristics. And the first thing is that if we look at how luminous the stars are, or how fast they're accreting, which is telling you how hot the disks are, that's correlated, sort of, with a hot water reservoir, but not with a cold water reservoir. If we instead look at the size of the disk, we see the expected anti-correlation. And though the paper is not submitted yet, I am happy to say that we now have 40 disks, and this is still holding up. That is that you see this anti-correlation between having a lot of water vapor and the disk size. So what does that tell us about habitability? Well, one of the things it tells us is that there's a lot of ways to get water into a terrestrial planet. You can have some of these icy pebbles drift in and not fully sublimate, but become incorporated into terrestrial cores. You can accrete the primary atmosphere that includes some water from all this sublimated water that ended up in the terrestrial planet-forming region. Or you can have impacts from comet and asteroid-like bodies that have all spent their whole time outside of the water snow line and are therefore very water-rich. The other thing to say is that it doesn't look like all terrestrial planets are going to form in the same water-rich environments. If you stop this inflow of watery pebbles, you're going to be in a much drier environment than if you don't. One way to stop it is to place a Jupiter-sized planet a little bit outside of the water snow line, which seems to be exactly what happened in the solar system. And it might very well be that that is actually necessary to, in some sense, to throttle or like to turn off most of the water delivery to not end up just forming a bunch of super Earths and mini Neptunes, but instead to just have this smaller, with just the right amount of water instead of having too much water. So with that, I want to turn to sort of the final vignette, which is about why we want the water in the first place, that is as a solvent for organics, and talk about the kind of organic chemistry that you expect to have in these disks. So I already told you that a lot of the chemistry that's going on we think is happening on grains. And that is also true for a lot of the organic chemistry. So our sort of main organic that we often end up focusing on is methanol. Turns out methanol forms very readily by starting with CO, having CO freezing out on the grain, and then adding hydrogen sort of one by one. So methanol often is present at sort of a 5 to 10% level compared to water in these icy grains. Once you have methanol, you can form tons of other kinds of organic molecules if you have some source of energy like a UV photon, an electron, or an X-ray. You just break apart methanol in different ways or add atoms to it and build up to form larger organic molecules. If we again go back to our schematic for how stars and planets form, if we look at the early stages of star formation, especially in this sort of protostellar stage, and we turn ALMA towards one of those and we take a rotational spectra, we get very rich spectra, where here most of the lines are not due to water, but due to different kinds of organics, including a lot of oxygen containing organics, as you would expect from this methanol-mediated chemistry. Do these organics survive formation of disks and planets, just like water does? Here, we don't have as much information from the solar system, including sort of D/H ratios. It's just more ambiguous whether the organics that ended up in comets in the solar system are truly inherited or came from some kind of disk or parent body chemistry. One of the reasons that you might expect some of these organics to not survive is that as these grains sort of flow through different phases, they're exposed to a range of temperatures, so you might just sublimate the ice. They're also exposed to a lot of energetic radiation that can break them apart. And many of these organics can be quite susceptible to being destroyed by photons. One of the ways that we investigate that is to go into the lab and design experiments where we try to simulate these interstellar ice matrices and then expose them to the kind of energetic radiation that you get during star and planet formation. Here, looking at benzene as one example, but you could put any of the sort of common organics that we find in space. We can deposit in the lab in very sort of thin layers, molecules thick, up to 100 molecules thick, and expose them to sort of the relevant radiation. One of the things we find is that it is quite dependent on what kind of molecule that you put in, how readily it is destroyed by photons. And it is not correlated to how readily it's destroyed in the gas phase. One example here is shown for hydrocarbons of different size, going from sort of C2 hydrocarbons up to benzene and benzene derivatives. These are pure or neat ices, so we're just deposited the hydrocarbon on its own. What you can see here is that the small hydrocarbons are destroyed pretty quickly. While things like benzene, we don't see any destruction when exposing the ice to kind of dose that we would expect in different astrophysical environments. So this is sort of interesting. We think a major thing that's going on here is a so-called cage effect, where if you think about the gas phase first, as sort of the fiducial case, if you have a molecule, you break a bond in the gas phase, those fragments will just fly apart. If you're sitting in an ice, and especially a stiff ice, and you break the same bond, those fragments might have a hard time getting away from one another, and you therefore have a pretty high likelihood of a recombination of those fragments. And that would explain why for sort of more volatile species, the ices are probably sort of softer, things can sort of fly apart more readily. You do see a large destruction cross-section, while for benzene, it's just a very stiff ice, so you're not going to see any net destruction, even though in the gas phase you absolutely would. This is reduced by at least 2 orders of magnitude compared to what you would expect from the gas phase. If we put benzene in a more astrophysically relevant sort of ice matrix, the kind of ices that are really abundant, This is a very different story. So this is again showing benzene destruction curves. You see the pure one, no destruction. And then we put it in a noble gas, not very astrophysically relevant, but good for physical understanding, CO, water, and O2 or CO2 ice matrix. And what we see here is that just by starting to isolate the benzene from one another, we immediately increase the photo destruction. What this is telling us is that even though the cage effect might be part of the story, it seems like maybe part of it was actually not the original two fragments recombining, but then finding sort of other fragments in the ice, and now we start to isolate the benzene from one another. That got a lot harder. But there's a second effect when we get to water, O2, and CO2 ice matrices, which is that you can also dissociate the matrix, and then those fragments attacks the benzene. And this is especially potent if you get an oxygen atom, as I'll show in some later experiment. This is all to say that it is difficult, just from theory, to predict how robust an ice is going to be to the kind of sort of destructive processes that you might expect to find. And we need, in addition to experiments, to develop sort of a model for how easy or difficult this is. We need observations that actually tells us what the survival is. One of the very clever observations that have been done have been led by Alice Booth, who looked for methanol in disks, but not in any disks. She picked disks around stars that are a bit more massive than the sun, and disks that are on average are much warmer than ours or solar nebula would have been. Too warm to contain CO ice. And remember, methanol mainly forms by hydrogenation of CO ice. So if there's no CO ice in these disks, then there can't be any in situ methanol formation. So if you see methanol, it must be inherited. And in about half of the disks, she does see methanol. And I realize these are not some nice pictures. That's because they are difficult observations. But if you, like, these blobs are all sort of coincident with where the dust is in these disks or right inside where the dust is sitting. This on its own is telling us that there is some inheritance of organics into disks. And once we know that, well, then we can go back in the lab and really start thinking about what else can be, like what will happen to these kind of organic ices. What other organics than the inherited ones should we expect to see in the disks? So I've already talked about a little bit about the experiments we do, but let me do a little bit of a more careful job in what one of these experiments look like. This is one of the chambers. Within the chamber, we have a cooled down substrate, around 10 Kelvin, where we build up ices that are analogs to these interstellar ices by depositing gas in a very controlled and slow way. So we build up ices that are pretty thin. Think 10 molecules thick, something like that. We can then expose these ices to the same kind of sources of energy that you have in astrophysical environments: heat, UV photons, electrons, X-rays, atoms, and so on. And then we have different ways to monitor how this deposition of energy, how that changes the structure of the ice, how it changes the dynamics of the ice, and how it changes the chemical composition of the ice. One of the mechanisms that we have been the most interested in looking at lately is how excited state atoms, radicals, and molecules can potentially drive a lot of the organic chemistry happening in these grains. Most of the time in an astrochemical context, we think about chemistry that happens between ground state atoms and molecules. And we do that because collisions are rare, which means that any excited state atom or molecule will have fallen down to its ground state before it meets another species. But in these icy grains, in some sense, you have already had the collision ahead of time. So you already have species sitting next to one another. And that means that if you excite one of them, you now suddenly can do a lot of chemistry at 10 Kelvin that we otherwise would not be able to do. Jenny Bergner pioneered this, did a bunch of experiments showing that if you have small hydrocarbons and you add this excited state oxygen atom, you form many new oxygen-containing molecules, like ethanol from ethane, but also acetaldehyde. If you have an unsaturated hydrocarbon, you will start to adding it to in this case, the double bond in addition to insertions. And if you start with something like acetylene, you get some rearrangement in addition to the addition. So we've been trying to explore how general this chemistry is. And one of the most recent experiments that's still ongoing is to bring together the excited sort of oxygen state chemistry with our nitrile kind of chemistry that we have seen previously in disks. So this was our attempt number one. So we were thinking about, let's just redo what we did for the hydrocarbons with acetonitriles. We just built up an ice with acetonitrile and oxygen. We irradiated it. That created the excited state oxygen atoms. And then we saw it react with acetonitrile. However, the same kind of irradiation that you need to break apart O2 also breaks apart the acetonitrile and any kind of organic product that you're trying to form, which makes for this sort of very messy kind of infrared spectra. And if you sort of squint, you maybe want to say that some of these new bumps here is due to this kind of strange new molecule, CH3NCO. But it is not something that you would publish as a secure detection. So we needed a way to isolate the oxygen insertion chemistry from everything else that UV photons can do to the ice. And what we decided to do was to install an ozone source and build up an ice that has ozone and acetonitrile. And then we can rip off an oxygen from the ozone with a much lower energy kind of UV photon, making the chemistry much more specific or isolated. So when we do that, we stop having all the gunk, and the only thing that we form is basically the CH3NCO molecule from this initial acetonitrile and ozone mixture. This is not the product we expected. We thought the methyl group on acetonitrile is basically like the methyl group on the hydrocarbons. We'll just get an insertion in one of the CH bonds. But instead, it seems like the oxygen prefers to attack the carbon and then do some rearranging to form this sort of preferred product. Interestingly, if we add, if we put this this mixture of acetonitrile and ozone in a matrix, and especially in a water matrix, we end up forming what looks like the alcohol over here. We don't know why that is. If it is because the water sort of helped stabilize that particular reaction, or if it is because you get some extra sort of hydroxyl radicals, if this sort of the excited state oxygen also attacks the water and forms some hydroxyl radicals. In addition to that, it's really neat that we can sometimes quantify this oxygen insertion chemistry by using ozone. I also just think it's pretty neat that we can start directing that chemistry by the kind of matrix that we have the chemistry happening in. So it's something that we're now seeing both with the destruction and the production, just how much sort of the matrix matters for the chemistry we're having. We see the same kind of insertion in benzene. I said that this was, I think, one of the explanations why we destroy benzene so effectively when we have an O2 or CO2 matrix. Here we're doing it again with ozone. I'm not showing it here because we're still trying to figure out what's going on, but we do seem to see also insertions into the carbon-carbon bond and additions to the carbon-carbon bond in benzene. So again, an interesting way to derivatize the molecules. The final thing I want to show is that things don't, even though most of the time we try to do this sort of controlled experiment where we're forming 1 or 2 or 3 products that we can quantify and really understand the mechanism, the chemistry doesn't stop there. If you continue to blast these ices, and you then take the residue of that ice and you bring them to your mass spec friend, you end up seeing mass spectra like this. So this just shows what happens when you start with a methanol and ammonia ice, two common interstellar ice constituents. And you see something that looks a little bit similar to what you get from a meteorite, let's say. You have a lot of these sort of large carbon kind of structures. You get rid of a lot of the oxygen by having a lot of UV photons being absorbed by this kind of ice. It sort of favor the carbon and nitrogen chemistry. We do find that it's pretty easy to make amino acids this way. This shows what happens when we take our non-isotopically labeled ice, and we see things like alanine, proline, valine, sort of the things that people have seen before, but generally needed to have a nitrile in the ice to form this efficiently. Seems like ammonia actually works pretty well as well to get to these kind of acids. One of the things we are trying to figure out is whether the sort of amino acid chemistry goes in different directions. If you have the nitrogen coming from ammonia, from N2, or from hydrogen cyanide, so three all common sort of nitrogen carriers in astrophysical environments. And I should say that we did redo this with isotopically labeled, and because we want to make sure this wasn't just our thumbprint on the little sample, and we do confirm that these are all forming in the ice. This is not the only thing that's going on in disks, however, and I want to finish just with a couple of slides on the gas phase chemistry that's happening in disks. I already showed you this before, this hydrogen cyanide, C2H, HC3N, formaldehyde, and so on that we see in disks. We think this is all happening through gas phase chemistry, where you have moved most of the oxygen from the gas into the solids, and you drive this pretty efficient sort of oxygen-depleted gas phase formation of nitriles and hydrocarbons. That is not enough. Also, in the inner disk, we don't just see the water coming in and getting dumped, we also see chemistry happening in the inner disk. And again, JWST is what we use to tell that. If we look at some of these spectra, I told you before, it's mostly water lines, but it's not just water lines. We see things like CO, acetylene, hydrogen cyanide, and CO2 as well in the inner disk. A lot of this, we think, comes from gas phase chemistry in the inner disk. One of the things that I think is the coolest that we're currently looking at is seeing how this chemistry depends on the sort of larger environment or larger context of this disk. So far, all the observations I've shown you are for disks that are sort of sitting on their own, which are the easiest disks to observe, but it is not the typical disk, and it's probably not our own history either. The solar system probably assembled fairly close to a massive star. These disks are all sitting close to a massive star in Orion, and you see sort of closest, close-ish, and further away, and you see both the physical structure around the disk as well as the spectra changing with distance. So what do we have? If we look at the organic chemistry in disks, we have some combination of things that are forming in the disk with things that are inherited. So you get this very nice sort of combination of sort of oxygenated kind of organic chemistry that's coming through this ice chemical pathway where all the oxygen is, and the gas phase chemistry, which is oxygen depleted, and therefore an excellent place to make these kind of oxygen poor molecules, again, nitriles, hydrocarbons, and so on. And then once these are made, they can also freeze out on the grain and become incorporated into comets and planets and so on. So if I sum up, we look at these distributions of molecules in disks, and we see that they vary a lot, which means that planets forming at different places are going to have different organic inventories. We see the elevated carbon to oxygen ratios in the gas that's producing a lot of sort of prebiotically interesting carbon-rich / oxygen-poor species. And we see this very effective grain surface chemistry, which can be directed in different ways dependent on how they're processed and what kind of matrix that the ice consists of. And bring it back to sort of the diagram that I've slowly been building up, when we think about the links between astrochemistry and planetary habitability, we can think about the chemistry either sort of instrumentally as a probe to understand this process, but also as the sort of main pathway that sets you up for the path towards life in the planet, whether we're thinking about the overall elemental reservoirs, water, or organics. And with that, I am happy to take any questions.